We present compact and optimal deep learning with recurrent parameter generators. The past few years have witnessed the exponential growth in the size of deep neural networks, as the growth in size usually comes with the growth in accuracy. Large networks are redundant and need to be compressed for practical uses. The common practice is that we search for the best model in a large model space with many parameters or degrees of freedom, or DOF, and then shrink the optimal model for deployment. On the contrary, our RPG starts from a lean model with small DOF, which can be unpacked into a large model with many parameters. We can let the gradient descent automatically find the best model under this DOF constraint. RPG use linear constraint neural optimization. Existing method directly optimize the whole network parameter in the space of W hat. We put the constraint on W hat, and then the actual space of parameter optimization degenerated to a plane. This accelerates the optimization and reduces the effective parameter size of DOF. We could put even more lower DOF constraint, and the actual optimization degenerates to a line. However, lower DOF may lead to lower accuracy. Here's the illustration of the linear constraint neural optimization. We see the large practical network weight W hat is actually generated with generating matrix G from the effective weight W, which is small. Our recurrent parameter generator, or RPG, is a special case of constraint neural optimization. RPG shares a fixed set of parameters as the model ring and use them to generate parameters of different parts of neural network. For example, at layer I, we use generation matrix GI to pull from the ring W and form the kernel KI. Unlike standard neural network, RPG parameters are coupled and reused, and the model set does not change as the layer goes deeper. Specifically, we ask the generation matrices G to be orthogonal to each other with random sign flipping and permutation. The orthogonal matrix G makes each kernel as dissimilar as possible. Another way to understand the intuition behind the orthogonal G is that we consider RPG as retrieval from the associative memory. Our RPG achieves extreme DOF compression with not much accuracy loss. For ImageNet classification, RPG achieves 96% of R18 performance with only 18% DOF. RPG also achieves 52% R34 performance with only 0.25% DOF. Empirically, accuracy and model DOF follow a power law for both CNN and VIT. The exponents of power laws are the same for R18 and 34 on ImageNet. The scaling law estimates the accuracy without training. RPG also enable under-parameterized model for large-scale datasets such as ImageNet, which may unleash new studies and findings. We found RPG performs better at the same model DOF for various tasks, including classification, post-estimation, and multitask regression. RPG can also be pruned and quantized to achieve lower inference time. It is on par with SOTA pruning and quantization methods. Empirically, we also found RPG converges much faster. To summarize, we propose new paradigm for compact and optimal deep learning. RPG directly optimizes a lean model with small DOF. It is faster and has high accuracy. Thank you.